So far we have been looking into designing the impulse invariant filters or IIR filters. There are three methods, and we have already looked into the method one, and it's an example, which is a pole zero placement. And it also happens to be your lab 2 exercise by using poles and zeros. How would one design an IIR filter? Now, moving on to the other examples, we have already looked into the methodology for method 2 of IIR filter design, which is the impulse invariant method. We will take an example, a quick example, just to show how things could be done from a mathematical perspective. So the impulse invariant method, as the name indicates, is essentially uses the concept of analog filter design to digital filter design conversion process. So here the filters are not really designed in the digital domain directly. We take advantage of the great designs available in the analog domain and transfer that into the digital domain. So what's given in this example is a simple analog filter by this transfer function. And transfer function in the analog domain is represented by a Laplace function or in S domain. So we have h of s equal to c divided by s minus p. So that's impulse response given for the analog filter. Now, to compute the impulse response in the time domain, I mean, what we say is the transfer function h of s, impulse from the time domain is h of t. And h of t is basically the inverse Laplace transform of your h of s. So when we do the inverse Laplace transform on the given example, then we end up in getting this notation, c times e to the power of p t. And it's a simple formulation for the inverse Laplace transform for the given function. But as per the inverse invariant method, we can get an equivalent digital version of it, if you remember, by doing sampling of this analog or continuous impulse response function h of t. Okay? Just like how we do sampling of the signals from analog to digital conversion, similarly, the h of t could be sampled in a way that we get discrete samples out of it, and they're equally spaced. And we need to design on a sampling frequency that needs to be selected here. Okay? But we do have that information of the sampling frequency because this is a design of a filter with a certain cutoff, and you have to sample at twice that cutoff. Okay? So if we were able to sample that and basically taking these discrete samples h n of tau, where tau is your sampling time, then we could get the discrete version of it by simple substitution of t equal to n tau. Okay. Now we are encountering a digital sequence here or discrete sequence. So it's straightforward now to do the Z transform on this h of n tau. And that's exactly been done here is by doing a Z transform on the discrete sequence. We get h of z, which is basically this time series function, or in other words, a polynomial. Okay. So very simple substitution and allows us to go from hs to hz. Okay. And that's essentially the impulse invariant method that was talked about in the second way of designing IIR filters. Now, that summation translates to be of this expression where it goes into the denominator, and you could very easily see we have a denominator notation here, which confirms the filter we are designing is definitely an IIR filter because it will bring in poles into the system. Now, if you look into this expression, it could be pretty easily expanded using partial fractions. So when we do a partial fraction expansion of the equation, then we end up in having a very compact representation of h of z. Okay, it's basically we have m of those partial fractions, and m again denotes here the order. In other words, we can also say that we will have m poles in the system. Okay. So that's kind of the simplest way of proceeding in designing a digital IIR filter from an analog IIR filter by using the impulse invariant method 2. Now, taking another example, just to confirm the concept that we learned, the method 3 for IIR design is based on the bilinear Z transform, or BZT. Bilinear Z transform is just a mapping of your S-plane to the Z plane. And when we do the mapping, it's normally not a linear mapping because the left-hand side of the S-plane gets mapped into within the unit circle in the Z plane. The imaginary axis in the S-plane gets mapped to the unit circle on the Z-plane. And the right-hand side of the S-plane gets mapped to the outside the unit circle of the Z-plane. And we have seen that graphical illustration before, and that's nothing but the bilinear Z transform method. So if you see, the mapping is not one-to-one linear, so we have to obviously look into something called pre-warping before we apply the bilinear Z transform methodology. So in this particular example that's been considered, we are required to design a digital equivalent of an analog filter, which happens to be an RC filter, a filter with a resistor and capacitor. And the sampling frequency that's provided to you is 150 Hertz. And the cutoff frequency expected of this filter is 30 Hertz. Okay. So the RC filter in the analog domain, from your previous knowledge, you can easily get an idea that this is nothing but the transfer function of this RC filter in the analog domain. Okay. Now, the cutoff frequency for the digital filter was given as 30 Hertz, and we can convert that into radians. When we convert into the radians, the key step, as indicated in the BZT, or the bilinear Z transform technique, to avoid any nonlinear effects of that mapping, is to do pre-warping. And the pre-warping is done by the formulation that was given to you before. And by doing the pre-warping, the new cutoff frequency is nothing but the tan of the old cutoff frequency, okay? Tan function of it. We have assumed that there used to be a constant k tan omega pt by 2. We assume the k to be 1. Okay? Now, the t is nothing but the sampling time, and it's 1 hour sampling frequency. So when you do that substitution, we are essentially designing this filter for a revised cutoff frequency of 0.7265. Okay? So these are basically normalized frequencies. That's why we use the sampling frequency to allow the normalization. And it's been normalized, and that's why you get 0.7265. And that normalization is happening because we already took the sampling time into the equation. So that's your new number. And all you have to now start doing is that just use the bilinear Z transform formulation. And here, the very first step is that we wanted to make sure in the S domain, we do the pre-warping, and the pre-warping is done by this substitution for low-pass filter is nothing S over the new revised frequency omega P1, just a simple substitution. So when we do that substitution for HFS, we end up in the new analog filter transfer function, which happens to be this one. Okay. So by converting this revised transfer function analog domain, we will avoid the phase wrapping that happens in the bilinear Z transform. And that's essentially been done here. Now that new HFS, we substitute the bilinear Z transform expression. Bilinear Z transform expression is nothing but making your S equal to Z minus 1 by Z plus 1. And in fact, we even saw how to derive that before. So when we use this BZT formulation, then it ends up in having a H of Z, which is given there. And we can always do some further simplifications. And now, once you have this H of Z expression, which seems pretty compact, you can always do the inverse Z transform of that. And inverse Z transform, you don't have to be too concerned here because we normally deal with the delay elements like Z minus 1 that really translates into a delay in the time domain. So it will be X of n minus 1, for example. Okay. So when we just do the inverse Z transform on the given transfer function H of Z, we end up in getting a difference equation, which is highlighted here. So now there you go. This is what we have calling that we have designed a digital IIR filter where the output of the digital IIR filter yn is represented by the equation that's provided there. Okay, and we go one step further. We could always tell that these are the filter coefficients. In other words, the filter coefficient A0 for the IIR filter is this one. The filter coefficient A1 is 1 because the coefficient that's here is 1. And the coefficient B1, which corresponds to the feedback, which is coming as a result of the yn, is this 0.1584. So we could also call these as filter coefficients. Okay, so that's what gets programmed and that's what gets implemented in the hardware are these numbers. So what's important at the end of the final IIR filter design in the digital domain are these numbers, 0.4208, 1, and 0.1584 are the important numbers. And as I've been telling before, we cannot afford to do any rounding or truncation operations on these filter coefficients because they will have an impact on the eventual performance. So we need to retain as much as possible the floating point and the double precision representation of the filter coefficients. Now, how it looks like in the hardware is this is what the analog filter that we started with in the method 3 example. And it's a simple RC filter. And so you can imagine this is a low pass filter because when you have the capacitor, which is here, it acts like a low pass filter. And an equivalent version of the digital filter, as we just discussed, involves the filter coefficients. So we have the filter coefficients here, and also this 1 is going directly into it. Okay. So to be more accurate, I think I should have made this x of n and this should be y of n. Sorry. So it's x of n because it's all happening in the digital domain now. So these are basically the digital filter coefficients, and this hardware configuration of RC circuit has been converted into a digital representation like what's shown here. Okay. So that's the neat thing about the design. I mean, yes, you're already starting to design filters in MATLAB, which is all software design. But at the end of the day, when we want to develop real world hardware instrumentation, you have the option to design a digital filter, which looks like this. So that's the idea here. With this example of going from an analog filter to digital filter by using the bilinear Z transform concept. Another simple example of a method 3 is essentially how do we go from a low pass design to a high pass filter. The previous example we just saw was going from a low pass analog filter to a low pass digital filter. Here, the interesting thing is that, yes, you are given a low pass filter in the analog domain. How would you go about doing a high pass filter? We have touched upon briefly this before, but it happens to be a very, very simple substitution in the pre-warping expression that will lead to that. And let's see through this simple, quick example. So this is the same filter that we saw before, analog low-pass filter that we saw before. Yes, we have to do the pre-warping that's needed to avoid the nonlinear effects. We did it, but the key substitution is in this area. So previously, because we wanted to go from a low pass to a low pass, we had the S equal to S over omega P1, but I am flipping that here. So omega P1 comes to the numerator and S goes to the denominator. By just this simple flip, the filter is now turned into a high pass filter design. Okay, so instead of cutting any frequencies above FC, the cutoff frequency, starting to pass any frequency above FC, and to cut any frequency that's below that. So it has been simply turned into a high pass design by that simple flip in the expression between the numerator and the denominator. So going through the same thing we saw before, we have all those things. Now this is what we saw before. So this would be the difference equation of a digital high pass filter for the given design problem, and filter coefficients are given here. And as I said, these are the important things to keep in mind are the filter coefficients. And so the number, for example, they're very, very important even in terms of the magnitude. For example, A0 is 0.5792, whereas A1 is negative 0.5792. So we can't even mess up with the signage there. You know, even a simple change of sign will have a drastic impact in the filter characteristics. Okay, so as much as possible, we should try to retain this thing and also program it in a way that the numbers are not being bothered. And also when you do a digital implementation in a microcontroller or a microprocessor, we have to ensure these numbers are fully retained. It also applies in some applications. We have to do a communication or a transmission of these coefficients to a remote location. And there also we have to make sure the communication channel does not impact the numbers. So a high fidelity of these coefficients is super important in digital signal processing, high fidelity. And that's a key concept. So the numbers, yes, in other areas we could do approximation, but we cannot afford to have an approximation done in the area of filter coefficients and filter design in the digital domain. Okay, so that's essentially very quick examples around the three methods of the IIR filter design. The reason why we had to go through the examples in the design processes is that it really gives you the first principles of a filter design problem. And it also allows you to basically visualize these concepts and apply these concepts when you're dealing with a real world situation, just like how I showed it, like how things get converted when we start to detect the physiological signal at the wrist level compared to at the ventricular level, you know, the QRS pulse, how it gets modified and things. So the body is going through some kind of a filtering process, and we are trying to understand what kind of a filtering process exactly is happening there. You know, in other words, trying to come with a transfer function of the thing, because once you know what's happening with the type of things that we see in the human body, then we can always develop systems which can detect any variations from a given number. Okay, so it happens like, for example, if these numbers that I showed you, let's assume it corresponds to a real world design of an ECG system that's showing how your filtering is happening between the ECG that's got at the wrist level compared to the chest level. Then if even the numbers modify slightly in your observation, that means you are probably entering into a territory of a pathological process. Okay, so you're getting a feel of it. So these quantitative numbers will allow us to do subsequent understanding of the system parameters, and it gets into the domain of data science and data analytics further. And obviously machine learning comes into play to basically detect these variations and any deviations in an automated way, so that we could flag that to the clinicians or to any caregiver about the variation, the number, which is what they will see at a very higher level, is that yes, something is changing and something is been deviating from a baseline observation. Okay, so again, I'm trying to bridge as much as possible the theory and the concepts that are available in the world of engineering. I'm trying to bring sense in the world of physiology and understanding human processes and any abnormality that might arise as a result of that. Okay? Now, so far in all this filter design things, we touched upon the essential idea of the frequency response of the filter, which is normally the magnitude response, because the frequency response does have real and imaginary parts. And when we take the absolute value, we are only interested in the magnitude response, which basically dictates your filter characteristics. Phase response, as I have been telling, is normally ignored in a lot of our analysis. It's just because it's very difficult to grasp any information extraction from the phase response. All we expect is that the phase response should have a linear response within the frequency range of interest. Okay, so if you have a frequency range that you're interested in, we expect within that frequency range, the filter to have a linear curve or a linear response, because it will have very minimal or no impact in the output that we are expecting. Okay, so just to show what I mean mathematically is that, as I indicated, we would like to have a linear phase response in the frequency of interest, or we could call it as a passband as well. So let's assume that we are passing a signal, a digital signal x of n, into a filter which has this kind of frequency response. So this frequency response, h omega, obviously is around the unit circle in the z plane, is a complex quantity. And we could also see the h of omega from the property of Fourier. In other words, h omega is nothing but y omega by x omega, as we have seen before. And I could rewrite that. And when I redo that, now the output, which is what yn, xn is the input and yn is the output. The output turns out to be a constant c times xn minus n naught. Okay? So this filter, if you see this filter, if you try to get the magnitude of h of omega, it will be 1 because, or in this case, it would be c, a constant, because the magnitude of this exponential function e power minus j omega n naught is 1. Okay, and obviously it has a phase of omega n naught. So that particular aspect of it, when we do the inverse Fourier transform on y omega, it tends to be yn is c xn minus n naught. Okay, so if you see here, a filter like this one obviously is not affecting the amplitude. It's just doing an amplitude scaling by a factor of c, and your input is purely delayed. It's delayed by n naught. That's all. Okay, nothing much is happening to your input signal xn. In other words, if you were to look into the waveform shape of xn, it's retained in yn. Nothing has happened to the waveform shape. Maybe the waveform shape would have been expanded or attenuated by a factor of c, or the waveform shape would have been delayed by n naught. Okay, so that's all we are seeing by this filter, and this is acceptable in a filter design problem. Now, how would this be a linear phase? Okay, the simple thing is that now we got that phase response, as I indicated before, is minus omega n naught. And if I were to compute the delay or the time delay, in some cases we also call it group delay if you have more than one frequency component. The simple thing is that we derive this phase response with respect to omega. When we do that derivative with respect to omega, then we find the whole thing is just delayed by n naught. Okay, so that's exactly it means it's a linear phase, because this function, if I plot it, the phase response, this function, when I plot it, it's a linear function, and this function, when it's derived with respect to the frequency omega, it gives a constant, and the constant is n naught, so it introduces just a constant delay element. Okay, and once you know that the filter has gone through this, it's just called a linear phase filter. Okay, so that's what a linear phase means. Okay, essentially, when you look into the phase response, if it has a linear characteristics with regards to omega, and we know it's linear characteristics only when we differentiate with respect to omega, it happens to be a constant, and definitely this function is a linear phase. So it might have a phase response like this. When we derive it, we got n naught, the delay response. Okay, so this is acceptable. This is tolerable in the world of filter design. And that's exactly what you would have seen in all the previous examples when we showed about the various moving average filters, the derivative filters. When we talked about IIR, FIR filter design, we always were looking into a linear phase representation. Okay, and at the end of the day, it does not do anything to the input xn, except that it might scale the amplitude, which is not a problem. Amplitude scaling and amplitude diminishing doesn't change the waveform shape or the morphology. Your QRS complex remains as a QRS complex, for example, with respect to the amplitude scaling. The delay is just shifting the signal by n naught. Okay, so both the things are acceptable in the digital domain, and we can overcome that. Like if we know something has been delayed by n naught, we could easily overcome that and make the process much more synchronized in real time. And that's exactly, some people call it as a latency in the system. Okay, definitely a lot of delay. When you know a lot of delay in the system, it means you have a higher latency. It means that delay variable n naught is quite high. Is it okay in some applications? Yes, other than a lot of the ICU, intensive care unit application, most of the other applications we see in biomedical signal processing, it could be done offline because we are trying to get information and insights, and waiting for a day or even weeks will not impact that much. But in ICU, yes, we need to do things in real time, and latency that we are talking about, the delay we are talking, should be quite low. Now, finally, this we have talked before also. We just looked into the example of how a low-pass to high-pass filter transformation should go through. But if you see this, what happens from a phase response perspective is that just by delaying the phase of your low pass filter by pi radians. Here I'm just delaying the phase response or the frequency response of the filter by pi radians. Okay, so this is a delay that's happening in the frequency domain, by the way. Okay, this is a delay because of the omega domain. By pi radians, I can get a high pass filter. So if I delay my low pass filter's frequency response by pi radians, if I use the delay pi radians, then I get the equivalent version of that high pass filter available to me. Now, when I do the inverse Fourier transform on that to get the time domain expression, the impulse response is nothing but -1 to the power of n, the low pass filter's impulse response. In other words, what happens with the filter coefficients that we derived with the low pass, you need to change the signage of the alternate coefficients, then you get the high pass equivalent. So that's why in one of the examples that we just saw, I was indicating to you, for example, in this example we just saw, the signage is pretty critical, okay? Because just by flipping the alternate signs, as you could see with this given notation, the whole filter, which was a low pass filter to start with, by changing the alternate signs has become a high pass filter. And the same thing applies vice versa. So if you have a high pass filter coefficients, if I change the signs of the alternate coefficients, I can get a low pass equivalent of that. Okay. So these are just simple tricks that we could play along with the numbers that we have to go from one filter to another filter. So before we look into how we really take all these filters together, so we are having some idea about the theoretical concepts behind the digital filter design. Very soon we will put them together in a very practical application, which also relates to what you are going to be doing in Lab 3. Before we proceed to that, I just wanted to point out another interesting and a simple idea of filtering called homomorphic filtering or deconvolution. Okay? Why this is needed? Because we are assuming so far in this course, we have assumed the filter or the noise that's added to the signal is always additive, okay? Is always additive, okay? In other words, if you have a signal X, we are assuming you have the noise added to that, that's called eta n, and this would be the output. So this is a noisy signal, okay? So the noisy signal, let's say Xn is your ECG, eta n is your random noise. It could come from various sources, instrumentation, other things, and Yn is a noisy ECG. This is assumption we made. The assumption we have made so far is that we are assuming that the process has gone through an additive process. Noise is additive. Okay. Noise is added. Noise is added. But in physical design, it's not designed in a way that everything will be additive. Okay. Just the additive, the summation expression is easy to analyze. So we have taken an easier assumption and have built all those filters. Okay. So when I know this is additive, then obviously when I use a low pass filter, we assume the noise to have high frequency, and this is gone. This is eliminated. Okay. That's what we have been doing, you know, by assuming things are additive. But as I indicated, practically we don't know. Well, there is a possibility your noise would be multiplicative, or your noise could be convolved with your signal of interest. All those variations are possible, and it's much more prominent in the domain of image analysis and image processing, where the pixels go through not necessarily an additive process, they go through other processes. So one way to address if your noise is not additive, if it happens to be multiplicative or convolutive, is by using homomorphic filtering. Okay, so we know when two things are for example, multiplicative. Here, let me switch over to a different notation. X of n is convolved with, let's assume h of n. Let's assume h to be noise, just for the sake of the notations here. When this is when this is convolution process, when the noise is convolved with your input or signal of interest xn, then how do we go about in removing this noise, h of n, for example? We know this convolution is a multiplication operation in the transform domain like Z transform here. Now, so yes, from convolution, I have gone to multiplication. Now, forget about signal processing here, just for a time being, think about simple mathematics. How would one go from a multiplication operation to an addition operation? Okay. So if you didn't get into the signal processing aspect of it, the way to go from multiplication operation to an addition operation is by using simple log. Okay. So when I apply a log on two multiplicative things, it becomes an additive concept. Okay. So that's exactly we are doing. We are taking a log on this y of z. When we do the log of this y of z, log y z, it becomes log x plus log h of z. Okay. Now it has gone back to whatever we have seen so far. So we have always designed our filters before for additive processes. Now we know how to get addition out of a convolution. Okay. So from convolution here, we have gone into addition here. From addition here, we have taken just a simple logarithm and come to a, from multiplication, by taking log, we have come to an addition operation. Okay. So just by using simple logarithmic operation on your process, which was multiplicative or convolved before that, we have come to an addition process. Once you know the addition thing, then we can, as I said, use other available filtering things and go with the classical ways of doing a low pass, high pass, or band pass filtering. Okay. So when we come to this level, you have to remember the major difference is that so far we have dealt with x of z and h of z without any issues. We know it's a complex quantity, but here the only difficulty mathematically, though log might be sounding as a simple operation, we are doing a log on a complex quantity. Log y of z is complex, and log of y of z is obviously a complex power series. Okay, so that's where there's a little bit of mathematical trick there, but not to be concerned. But from a number representation point of view, if you're just interested in the magnitude response of the system, we can always take the magnitude of this one and just work on the real quantity. Okay, which solves most of the thing. As we know, magnitude response will do most of the thing for us, and we can not worry about phase response. So if that's the case, taking a magnitude will do the job for you, and you will get the equivalent thing going in the magnitude domain. So this happens to be, just if I do an inverse now from mathematical number representation point of view, this is nothing but a series of numbers in the Z domain, and now I can easily do an inverse Z transform on that, which is basically a log compressed, and I can get back this. So now I come back to an additive process, and we could use any type of filtering here to either get my X or get remove of my H, whichever I want. Okay. So this idea, homomorphic filtering, it's also called deconvolution, is essentially because you see, I deconvolved. If previously we have seen convolution expression, the convolution, if this is your impulse response, your input gets convolved with impulse response. By this process, if I am removing my X from H, then again, we could also see this as a process where the convolution is being removed. In other words, if I just filter this out and I'm getting my X, the H, which was causing the convolution before, is been removed. That's why it's also called deconvolution expression. Okay. It becomes quite important, this idea of homomorphic filtering. If you remember a couple of lectures ago, we touched upon briefly a concept called inverse filtering. Okay. So an inverse filter is similar to a deconvolution operation. Is essentially you're trying to extract your signal X by observing Y. Okay. You're trying to extract your input by observing Y. Okay. So that becomes pretty important in a lot of our signal interpretation operations, because if you see, going back into what I'm just telling now, so yes, in many cases, we take the input X, we go through H, which could be a filter, and we modify it to give Y according to what we need. The idea here is that let's assume you are a handle of Y and you want to go back to X. And previously I mentioned about an inverse filter where all we did was flipping the transfer function from h of z to 1 over h of z. So if the input to this filter 1 over h of z is y, then obviously the output we get is x. So I can recover my x through this inverse filter. That's exactly happening in this homomorphic operation as well, where I am getting back my x from the given observation y. And knowing x, typically the input to the system has a lot of physiological significance. Okay, and you will get to appreciate this more as we go along, is that in many cases when we are operating on y, it happens to be a case where the things are either distorted version of x or amplified version of x or other modifications on x. So to know what those modifications, to recover back the deconvolution process or the inverse filtering process comes in quite handy. Okay. So in a nutshell, the deconvolution or inverse filtering is to know the effect variable and get the causal aspect of it. What is causing something could potentially be revealed through the process of deconvolution and inverse filtering. And again, this same idea which we talked so far is that if your noise happens to be multiplicative, then we can take multiplication to an addition operation by using log. And from the log, when we have the addition operation, then we can go back to the classical filtering that we have discussed so far and apply those filters. When your process is convoluted, then convolution, going from convolution to addition takes one intermediate step. Convolution has to be converted to multiplication, and that could be done in the transform domain, like taking the Z transform. And from that Z transform, when it becomes multiplicative, then we can always do the log to convert additive. So that's kind of just playing around with the arithmetic operations and getting the various filters designed so that we can overcome anything that's beyond addition operation. Okay. Now, other type of influence in the signal other than addition, multiplication, convolution, for sure. I think that's where the gaps are. That's where we need the contribution from people in engineering to help us remove when we know the noise is impacting the signal beyond addition, multiplication, and convolution. Then we need other innovation and ingenuity from people like you to design filters which can help us to overcome those difficulties. Okay, so but having said that thing, I think the three operations that I just mentioned, with that understanding, we are able to solve most of the interference and noise related problems. And we are also starting to get some idea about the filters behavior by using the idea of deconvolution. Okay, so with this, if there are any further discussions, obviously we will expand that when we take a practical example of applying these concepts in the domain of a real world example, which would be very soon covered. And that example would also be the basis for the lab, where we will go through the series of the filtering operations we discussed in analyzing one of the most important aspect of biomedical signals, heart rate. Okay? So we will come back and discuss about how we go about it, doing heart rate estimation and estimating how the heart rate plays an important role, not only in understanding the physical health and also in expanding that into psychological and mental health aspects of the human behavior. Thank you.